Hello, folks. So this is going to be a discussion of a kind of an old school device called an oscilloscope, which is what this thing is right here. And I'm doing this kind of unscripted, so we'll see how it goes. Basically what an oscilloscope is a glorified voltmeter. So if you think about what voltmeters do for you, you take the leads of the voltmeter and you put it across the element that you want the voltage difference across, and it tells you what the voltage difference is across the element. You can put it across a power supply and it will tell you what the voltage difference is between the terminals. You put it across a resistor and it tells you what the voltage change is on either side of the resistor. That's what voltmeters do. This, as I said, is kind of a glorified version of that. And they're actually very clever devices. It's effectively an electron gun. So essentially what it's doing is it's shooting a beam of electrons toward the screen that will fluoresce if electrons hit it. And if that was all that was going on, what you would see in the middle of the screen would just be this little dot, because that's where the electrons would be hitting. Now, it turns out that inside you have two sets of plates. You have plates that are set up like so, and you have plates that are set up like so. The plates that are set up like so generate an electric field that varies both in magnitude and direction. So let's say that at a given instant, the electric field is in that direction, and it's very, very big. What's going to happen is that the beam of electrons are going to come in. They're going to be accelerated opposite the direction of the electric field, because that's what electrons do. And the beam is going to get bent so that it's going to hit the screen over here. If that field begins to diminish in size, the bending will be less. And if it continues doing that over time, the beam will go less and less and less and less and less. And the effect will be is that that little dot will actually move across the screen until it gets to the dead center spot, at which time the direction of the electric field changes. Now it's going this way, and it's practically nothing, and it starts getting bigger and bigger and bigger. So the electrons are in this position. Now they're starting to feel a field that is pushing them this way, because the electric field's that way, and it's just pushing them a little bit, and then as the field gets bigger, it pushes them more and more and more. And so effectively what ends up coming down is this varying electric field between these plates makes this little dot sweep across the screen. And that's exactly what you're seeing right now. Okay, I have this thing set up so that that's what it's doing. Now, if that's all that it was doing, that would be cool. Not very useful, but cool. You can vary the speed of that little beam, though. Okay, and the way that you do that is with an adjustment. I'm going to disappear here, but I'm going to show you where it is. There's an adjustment right here that will allow you to change what's called the sweep time. So it's the number of seconds per centimeter. So I picked it up, and I'm picking it up now a little more, and 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 a little more. Right now, I'm sweeping at about 1 millisecond per centimeter. Okay, and the consequence is that it ends up giving you a line. Okay, which is great. Okay, that's exactly what we want. We want to be able to have something that gives you not just a dot, but what appears to be a line, as a consequence of the fact that the electrons are sweeping across so fast that they give you the effect of a line. Okay, now, what's going on with the plates that are set up like so? Okay, so that has to do with the input. So right now, there is no voltage across these plates. But if I were to go ahead and take, like, say, a 9-volt battery, which I just happen to have here, and I might add, this is a really old 9-volt battery, so it probably isn't chugging away at 9 volts anymore. But if I were to go ahead and do that, and take the voltage difference between those terminals and put it across these plates, what that would do is it would generate an electric field in the vertical. So along with the beam sweeping across like so, there would also be an electric field that would either make the beam go up some distance or go down, depending on how the polarity was set up. And so instead of sweeping along this line, it would be maybe sweeping along this line. And if you knew how many volts were associated with some number of centimeters of upsweep, you could figure out what the voltage was. So I have, here are the inputs. Here's the place where you put the information in. Here are my leads. I am going to go ahead and I'm going to move this down so it's fairly low, sweeping across this line right here. I'm going to put this on 1 volt per centimeter. So if it jumps up 1 centimeter, it means this thing only has 1 volt associated with it. This is the high voltage side, so I'm going to go ahead and put this like so, and I'm going to touch this like so. Let's say touch this like so. Oops, sorry, I have to put that on DC to let the oscilloscope know it's measuring a DC source. And so it goes from there to there, which is about a 6 centimeter jump. So there to there, it's about 6 centimeters. So apparently, this battery it's got about 6 volts at this point across its leads. Okay. A glorified voltmeter. Now, if that's all these things did, who would spend the money on them? Because you can use a voltmeter that looks like this just as well to figure out what's going on across something like a battery. Where things get exciting is if you're dealing with AC. Because in a situation with AC, the voltage, if you will remember, this could be the high voltage side for a while of the terminal, and then this terminal could be high, and then this could be high, and this could be high. And it's going to alternate. The voltage is going to alternate. And so if we took our leads and we put it across an AC source, what's going to end up happening is that this electric field is going to alternate, and the beam, as it's going across, is going to alternate. And so I have here a power supply that I pre-set up to 425 cycles per second. I'm going to go ahead and plug the high voltage side here and the low to here, and presumably you're not going to see the whole little guy here because I have to swing him up. But if I do, okay, so there you can see what's happening is that the voltage is changing. The plates are oscillating of this electric field, and it's oscillating back and forth and back and forth and back and forth. A couple of tiny little points of order. The first has to do with what's called peak-to-peak voltage, amplitude, and RMS value. So the peak-to-peak voltage is the voltage from one peak to the other. So the peak-to-peak voltage looks like that. You can't see it because of the lights. So let me move this over just a bit. Not going to work. Okay, let me do it over here. So peak-to-peak voltage, and the thing is oscillating like so. If you go from one peak to the other, that is called the peak-to-peak voltage. If you look on the oscilloscope, you will see that we go from here up to here, that's 4 centimeters, and I'm on 1 volt per centimeter. So apparently, in this particular case, we have 4 volts peak to peak. The amplitude of the wave is measured from the equilibrium position up. So this is V naught, which is half of the peak-to-peak voltage. So the amplitude in this case is 2 volts. If you will remember, the RMS value for an AC source is 0.707 of the amplitude. Which means in our situation, we have 0.707 of 2, which is what? 1.414 volts. So, if I were to go ahead and take a voltmeter, and hook it across, and put it on the 2 volt range in the AC range, and go ahead and put it across this source, it ought to be measuring somewhere around 1.4 volts. And in fact, it does. Okay? And it's not dead on, but that's not too surprising because this thing is probably not exactly 4 volts peak to peak. So the point here is, okay, meters measure RMS values. You can take the information that you need to be able to figure out the RMS value off of an oscilloscope. Now, you can also obviously take it off of the meter, but the point is that if all you have available to you is an oscilloscope, you can get it from an oscilloscope also. Which is kind of a side point, but kind of important. And it's actually going to be important in a lab that you're going to be doing down the line. Okay, so at this point, we now have this line that is moving across the screen, which is nice, but not terribly useful. If you think about it, though, what's really going on is that the beam is doing this as it's going across. If we could speed the beam up, or I should say if we could speed the sweep up, what would happen is that you would start to see the sine wave that was associated with the motion. So I'm going to go ahead and I'm going to take the adjustment that allows me to speed things up. And you should be able to see, let me make it a little darker, you should be able to start seeing. So let me go back because it wasn't dark enough. It's going slow. I'm going to make it go faster, 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 faster. And you will finally be able to actually get the waveform physically showing itself on the screen. And from this, once again, if you had to, you could measure the peak-to-peak voltage from which you could get the amplitude, from which you could get the RMS value for that source. Okay, you could do all of that. And again, this is something you're going to have to do in a lab that's going to be coming up here pretty soon. Now, the other thing that I want to point out before I let this go, actually there are two other things I want to point out. The first is that you can also figure out what the frequency of the source is by looking at the information on the oscilloscope. So the sweep time here is measured in seconds per centimeter. So seconds per centimeter means that if I go ahead and measure the number of centimeters in one full cycle, which is going to be associated with the period of the motion, let me move this thing, move it over, let's see. So this guy is right here, so I go 1, 2, 3, 4, about 4 point, this is not quite over, I'd say about 4.7. I need to move it. This oscilloscope is quite old, and it probably needs to be cleaned, so it's a little bit hard to do this, but I'd say about 4.7. And I'm on the 0.5 times 10 to the minus 3 seconds per centimeter. So notice, if I take the 4.7 centimeters, so this is like the wavelength in centimeters, and I multiply it by the 0.5 times 10 to the minus 3 seconds per centimeter. So this is the sweep time. If I take my calculator and I do all of that, so I've got 4.7 times 0.5 e to the minus 3. I'm going to get 0.00235. And the units are going to be seconds, basically. If I flip this over, I'm going to get the units of inverse seconds, which are the units of frequency. In other words, basically what I just figured out is the period. This is effectively seconds per cycle. Okay. If you flip it over, you're going to get the units of cycles per second. So if I flip this over, I get 425.5 cycles per second. And if we look on the source here, it reads 425.2 cycles per second. So another thing that you can do, if you have to, and this is something that you had to do in the old days, because in the old days we didn't have digital function generators. You had generators that had analogs, you rotated a knob, but you didn't really know what the frequency was. You had to figure out what the frequency was somehow. And the way you figured it out was like so. You counted the number of centimeters in the waveform for one cycle, and then you multiplied by the sweep time, and then you inverted it. Anyway, this is the way oscilloscopes work. You're going to be hooking up two different sources. There are two different inputs with this thing. You have two different channels. So I only have it on channel A, but I can put it on for both channels. So this is the information coming in for channel A. This is the information coming in for channel B. There's nothing coming into channel B, so it's just blank. But you're going to actually do a lab in which you're tracking what's going on from the power supply coming into channel A, and you're tracking what's happening in the circuit in channel B. It should be a very fun lab to do. I'm actually looking forward to setting it up and writing it. Anyway, that's pretty much all I have to say for this. As I said, you're going to have the thrill of using an oscilloscope down the line for a lab. Hopefully you'll have some kind of clue as to how it works, because, I mean, clearly I'm going to be the one that's going to be doing the manipulating, but at least you'll know what you're seeing when the time comes. So that's it.